Most people are afraid of nuclear power. The people who understand it are afraid of losing it. For decades, nuclear energy has been framed as dangerous, unstable, and catastrophic. Images of explosions, meltdowns, and disaster dominate the narrative. But the reality is different. Nuclear power is not primarily a story about destruction. It is a story about density, energy density, stability density, infrastructure density, and scale. To understand nuclear power, you have to understand one simple fact. Uranium contains more usable energy per kilogram than almost any other fuel humanity has ever touched. A single uranium fuel pellet the size of your fingertip contains as much energy as 1 ton of coal. That is not a metaphor. That is physics. Energy systems are not moral. They are mathematical. And mathematically, nuclear power is one of the most concentrated, efficient, and scalable energy systems ever built. So why is it feared? Because when nuclear systems fail, they fail dramatically. But here is the overlooked truth. Modern nuclear reactors are among the most regulated, redundantly engineered, and statistically safe industrial systems on Earth. The fear is psychological. The system is structural. Let's break it down. Electric grids require something called baseload power. Baseload power is the constant, steady supply of electricity required to keep a modern civilization running. Hospitals, data centers, manufacturing, water treatment, transportation infrastructure. These systems do not function intermittently. They require stability. Solar and wind are powerful technologies, but they are variable. They depend on weather conditions. Nuclear reactors do not depend on weather. They run continuously, day and night, for months at a time, with refueling cycles measured in years, not days. That stability creates leverage. Leverage creates reliability. Reliability creates economic productivity. This is where nuclear becomes misunderstood. Most people view nuclear energy as a risk. Engineers view it as an anchor. France understood this decades ago. Today, roughly 70% of France's electricity comes from nuclear power. As a result, France has some of the lowest carbon emissions per capita among industrialized nations. It also has stable energy pricing compared to many of its European neighbours. That was not an accident. It was a systems decision. Nuclear plants are expensive to build, very expensive. But once operational, their fuel costs are relatively low, their output is predictable, and their lifespan can extend for decades. That makes nuclear power a long-term infrastructure investment, not a short-term profit play. This is one reason many private energy markets underinvest in nuclear. The upfront capital requirements are enormous. Regulatory processes are slow. Public sentiment is volatile. Political cycles are short. But energy infrastructure is long. That mismatch creates stagnation. Now consider the alternative. Coal plants emit massive amounts of carbon dioxide. They contribute to air pollution. They require continuous fuel transport. Oil and gas, cleaner than coal in some cases, but still carbon-based, still finite, still geopolitically sensitive. Renewables, essential, growing rapidly. But storage remains the constraint. Battery systems at grid scale are improving, but they are not yet sufficient to replace stable baseload entirely. Nuclear fills that gap, quietly, without combustion, without continuous refueling convoys, without direct carbon emissions during operation. The word nuclear triggers fear. But the data tells a different story. When measured by deaths per unit of energy produced, nuclear power is statistically safer than coal, oil, and even some renewable categories when manufacturing and life cycle effects are included. Chernobyl and Fukushima are invoked as proof of danger, and they were catastrophic, but they were also system failures under specific conditions. Chernobyl involved a flawed reactor design and severe procedural violations. Fukushima involved a massive earthquake and tsunami that overwhelmed backup systems. Modern reactors are not built like Chernobyl. Safety protocols are not what they were in 1986. Passive safety systems now exist. Some reactor designs can shut themselves down without human intervention or external power. Gravity, pressure, natural physical processes, engineered into the core. The irony is this: the same physics that makes nuclear powerful also makes it controllable. Chain reactions are regulated. Control rods absorb neutrons. Containment structures isolate core activity. Multiple redundant safety layers exist. Nuclear engineering is obsessive by necessity, because the cost of failure is high. That obsession has made it one of the most scrutinized industrial domains on Earth. There is another layer to this conversation: energy independence. Countries that control stable domestic energy production reduce their exposure to geopolitical volatility. Oil supply chains are global, gas pipelines cross borders. Renewables depend on rare earth materials and supply networks. Uranium, by contrast, is extraordinarily energy-dense. A relatively small amount can power massive infrastructure, and fuel can be stockpiled. That reduces vulnerability. This is where nuclear power becomes strategic. It is not just about electricity, it is about resilience. Now consider small modular reactors. SMRs are being developed as compact, scalable nuclear systems. Instead of massive multi-billion-dollar plants, smaller reactors can be deployed incrementally, factory-built, standardized, transported, and assembled. This changes the economics. Instead of one massive capital commitment, infrastructure can scale gradually. That mirrors the logic of cloud computing: modular deployment, redundant capacity, distributed resilience. If successful, SMRs could shift nuclear from centralized mega projects to distributed infrastructure systems. But adoption requires political will and public trust. Public trust is fragile in the nuclear domain because nuclear is invisible. When a coal plant runs, you see smoke. When oil burns, you see flame. When nuclear generates electricity, nothing is visible. That invisibility paradoxically increases fear. We distrust what we cannot see, but invisibility is not instability. It is containment. Nuclear waste is often cited as the ultimate objection, and yes, radioactive waste exists. But here is the scale comparison. All of the high-level nuclear waste produced by the United States over decades could fit on a single football field stacked a few yards high. That is not infinite, it is finite, and it is contained. Coal waste, by contrast, disperses into the atmosphere continuously. Invisible does not mean absent, it means dispersed. Nuclear waste is concentrated, contained, monitored. Long-term storage remains a policy challenge, but it is a management problem, not an exponential one. The fear of nuclear is amplified by association with weapons. Fission physics powers both reactors and bombs. But the systems are different. Weapons are engineered for rapid, uncontrolled release. Reactors are engineered for slow, controlled output. The same underlying science. Different system architecture. That distinction matters. Now zoom out. The global demand for electricity is rising. Artificial intelligence, data centers, electric vehicles, industrial electrification, population growth in emerging markets. All of it increases grid pressure. Energy demand is not static. It compounds. If energy demand compounds, supply must scale. If supply must scale, systems must be stable. Nuclear is one of the few systems capable of producing massive, stable output without direct carbon emissions. And yet construction rates have stagnated in many countries. Why? Because nuclear requires long-term thinking, and modern political systems are short-term oriented. Quarterly profits, election cycles, immediate public sentiment. But infrastructure does not operate on quarterly logic. It operates on decades. This is the core misunderstanding. Nuclear power is not a technology decision. It is a systems decision. Do you prioritize stability? Do you invest upfront for long-term resilience? Do you accept visible fear in exchange for invisible reliability? Countries answer those questions differently. Germany chose to phase out nuclear power. France chose to double down. The United States remains divided. China is building aggressively. These are not purely environmental decisions. They are strategic architecture decisions. Nuclear power is not perfect. No system is. It carries risk. It requires oversight. It demands engineering rigor. But so does aviation. So does pharmaceuticals. So does financial infrastructure. The difference is perception. Nuclear risk feels existential. Coal risk feels routine. But routine risk often kills more quietly. Energy systems determine the ceiling of civilization. Without stable electricity, digital infrastructure collapses. Without stable grids, economies slow. Without energy density, industrial productivity declines. The conversation around nuclear is often emotional, but the system is mathematical. High energy density, low operational emissions, stable baseload output, long asset lifespan, capital-intensive upfront investment, strong regulatory constraint. That is the trade-off. The question is not whether nuclear is dangerous. The question is whether the alternatives are more stable at scale. Because the future grid will not shrink. It will expand. Artificial intelligence alone requires massive data center capacity. And data centers require continuous power, not intermittent. Continuous. If we want low-carbon grids, if we want energy independence, if we want resilience under pressure, nuclear remains one of the most scalable anchors available. The irony is this: the more complex our civilization becomes, the more we need dense, stable energy systems. And nuclear is dense, extremely dense. It is not optimized for optics, it is optimized for physics. And physics does not negotiate. Most people fear nuclear power because they associate it with catastrophe. But systems engineers evaluate probability. Engineers calculate risk per terawatt hour. They compare life cycle emissions. They analyze redundancy. They model failure cascades. From that perspective, nuclear is not irrational. It is disciplined. Energy debates will continue. Technology will evolve. Fusion research may one day redefine the equation, but right now, nuclear fission remains one of the most powerful infrastructure tools humanity has built. And abandoning it entirely is not a neutral decision. It is a systems gamble. Nuclear power is not about glow-in-the-dark myths. It is about density, stability, and long-term scale. If we remove the emotion and analyze the architecture, nuclear is not chaos. It is control. And in a world that increasingly depends on uninterrupted power, control may matter more than fear.